Hi, Assalamualaikum. This video is the continuation from the previous lecture, which is Parallel Programming Platform Part 2. This video actually will continue from the slide number 31 until the end of the slide. So in this subtopic, it is about the alternate approaches for hiding the memory latency. So previously we already discussed about the latency that faced by the parallel computing. Okay, so how to hide the memory latency? So please consider the problems of browsing the web on a very slow network connection. So we deal with the problem in one of the three possible ways. The first one, we anticipate which pages we are going to browse ahead of time and issue requests from them in advance. So that one is the first way. And then another one, we open multiple browsers and access different pages in each browser. Thus, while we are waiting for one page to load, so we could be reading the others. So this one is the second way. And the third one is we access a whole bunch of pages in one go, amortizing the latency across various accesses. So there are three ways. The first one actually the situation by using pre-fetching approach. The second one is by using multi-threading, and the third one is actually by using special locality. Okay, all right. So a thread is a single stream of control in the flow of a program. So we will illustrate the threads with a simple example. So we have for loop here, okay, but the first one actually without using any thread, okay, just call the method dot product. Okay, so each dot product is independent of the other. So assume that dot product is an independent and therefore represents a concurrent unit of execution. So we can implement a concurrent execution of dot product. We can safely rewrite the above code statement as follows. So you write back the for loop and then call the method create thread inside the bracket. We include back the dot product method and then get row method. So in this case, this code implements a multi-thread or thread process. Okay, so let's look at the description at the next slide. So in the code, the first instance of this function accesses a pair of vector elements and wait for them. So in the meantime, the second instance of this function can access two other elements in the next cycle and so on, which means in one line of code, there are three execution can be done. So after L units of time, where L is the latency of the memory system, the first function instance gets the requested data from memory and can perform the required computation. Then in the next cycle, the data item for the next function instance arrive and so on. So in this way, in every clock cycle, we can perform a computation. There is no latency, or we can hide the latency by manipulate the looping just now. Okay, all right. So the execution schedule in the previous example is predicated upon two assumptions. So the first one is the memory system is capable of servicing multiple outstanding requests. And the second one is the processor is capable of switching threads at every cycle. So in order to implement this kind of implementation execution, so we need to consider and assume that the memory is enough, okay, to perform the multiple requests, and then the processor also is capable to switch threads at every cycle. Okay, so it also requires the program to have an explicit specification of concurrency in the form of threads. So we need to know whether the program, okay, have an explicit specification to perform the concurrency. Okay, in this case is threads. Mentions such as the HTTP and Tera rely on multi-threaded processors that can switch the context of execution in every cycle. So these are the example that implement multi-thread, okay, and then to hide the latency effectively. Okay, so let's look at the prefetching for latency hiding. So this situation misses on loads cause programs to stop, which means the program might be delayed if we miss on the loads. So why not advance the load? So the other alternative, instead of miss the loads, so we reload it in the earlier stage. Okay, so that by the time the data is actually needed, so the data is already there. So that one is what is meant by pre-fetching. The only drawback in this concept is we might need more space to store the advanced loads because of what we do the prefetch. We prefetch in earlier stage, so we need a memory to store the loads or data. So however, if the advanced loads are overwritten, we are no worse than before. So actually, if the data is overwrite, okay, so actually it's not a big problem for us to implement pre-fetching. Okay, so trade-offs of multi-threading and pre-fetching. When we implement multi-thread and prefetching, actually is really give an impact to the memory bandwidth. Even though we can reduce the latency of time, the processing time, but actually it's increase the memory bandwidth. So let's consider the following situation. So we have two cases here where these are the description of the memory and also the bandwidth. Okay, so first situation is a single threaded execution in which the entire cache is available to the serial context. This one is implementing the serial processing. And the second case is a multi-threaded execution with 32 threads, with where each thread has a cache residency of 1 kilobit. Okay, and then if you can see here between these two cases, the implementation of multi-threaded requires large bandwidths compared to the first case, which is using a single threaded execution. Okay. All right. So bandwidth requirements of multi-threaded system may increase very significantly because of the smaller cache residency of a thread, because we implement many uh, processor or concurrent processing at the same time. So it requires more cache, even though the cache has a smaller size. So multi-threaded system become bandwidth bound instead of latency bound. Okay, so this is the trade-off, the multi-threaded, the limitation of multi-threaded. Instead of getting faster in the processing time, but it's required more or large bandwidth during the execution. So multi-threading and prefetching only address the latency problem and may often exacerbate the bandwidth problem. So multi-threading and prefetching also require significantly more hardware resources. So due to this, to overcome the problems of bandwidth just now, so maybe it require more resources in terms of hardware to store or to have the data storage. Right. So next one is dichotomy of parallel computing platform. So dichotomy also is known as differences. So we want to look at what are the types of model that can be implemented to apply parallel computing. So an explicitly parallel program must specify concurrently an interaction between concurrent subtasks. Okay, so this is the concept that we need to know uh, that related to parallel computing. So the former previously, okay, a long time ago, how to control the concurrency or to make the parallel computing execute. So it is called as control structure. So later now we are calling the control structure as communication model in terms of how does the parallel the processing element being communicate with the memory. So we want to look at there are several models that can be used, okay, but actually we need to look at uh, the number of hardware and algorithm or even the component that we use to construct our parallel computing platform. All right, so control structure of parallel programs. Parallelism can be expressed at various levels of granularity, from instruction level to the processor. So we actually this parallelism actually can be discussed or can be implemented, can be applied in various levels, so such as in instruction level or even to the processes. So between these extremes exists a range of models. There are many models being introduced by the manufacturer. So along with corresponding architectural support. Alright, so processing units in parallel computers either operate under centralized control of a single control unit or working independently. So it has two approach, either centralized or independent. So if there is a single control unit which is centralized that dispatches the same instruction to various processors, that work on different data, this model is called as single instruction stream, multiple data stream. Okay, it has one instruction but consists of many data. Okay. If each processor has its own control unit, each processor can execute different instruction on different data. So, processor has its own CPU control unit, and then it can execute on different kind of data. So this one is called as multiple instruction stream, multiple data stream. Okay, let's look at the diagram of this SIMD and also MIMD. So A is represent the single instruction multiple data stream. Meanwhile, B represent the multiple instruction multiple data stream. So as you can see here, the difference between these two processes, the MIMD consists of its own control units. Okay, okay, and then A, the single instruction using the global control unit to control the whole or all the processes that execute the parallel computing or execute the concurrent process. Okay, so let's look at the SIMD processes. Okay, so the first one is the earliest example. What are the processes that implements SIMD, such as ILIAC, 4, MPP, DAP, and so on. Okay, so variant of this concept has found use in co-processing units such as MMX unit, in Intel processors, and DSP chips such as the Shark. Okay, SIMD relies on the regular structure of the computations, such as in image processing. So it is often necessary to selectively turn off operation on certain data items. So for this reason, most SIMD programming paradigms allow for an activity mask, which determines if a processor should participate in a computation or not. So some of the operation might be turned off. Okay, not necessary to turn all the processor. So this one is SIMD. Alright, so this is the example how the conditional execution is being implemented in SIMD processor. So you imagine they want the A is the conditional execution structures that will be implemented or execute into steps. Okay, so it will execute the data or the conditional execution one by one, step by step. Okay, until we get the result. Okay, so let's proceed to the MIMD processes. So actually MIMD processes is the control of SIMD. It can execute different programs on different processors, multiple instruction, multiple execution, okay, multiple data stream. A variant of this, a variant of MIMD is called as SPMD, also known as single program multiple data stream, which execute the same program. Single program is also known as single program on different processors. It has more than one processors. So it is easy to see that SPMD and MIMD are closely related in terms of programming flexibility and underlying architectural support. So both SPMD and MIMD actually can work together or has a similar kind of execution. Okay, so example of platform that use SPMD or MIMD, Sun Ultra servers, SGI Origin servers, and others. Okay, or even workstation clusters and also the IBM SP implement MIMD or SPMD. Okay, so let's look at the comparison between SIMD and MIMD. Okay, if you are using SIMD, you require less hardware compared to MIMD computers because it has more processors. So, however, SIMD processors are specially designed. They tend to be expensive and have long design cycle. Okay, because it's used a single control unit. Not all applications are naturally suited to SIMD processors. So in contrast, platforms supporting the SPMD paradigm can be built from inexpensive off-the-shelf components with relatively little effort in a short amount of time. So to overcome the SIMD, so SPMD can actually uh, cover all the processes. So as you can see here, I already summarize the weaknesses or the description about the SIMD and MID. So SIMD use less hardware but it's quite expensive, and then it's cover the specific tasks and have long design cycle. However, MID require more hardware but less expensive because it can just implement or use the existing processes and then can be connected through network, and then small effort in less time because it run at one time. Okay, so next, so let's move on to the communication model of parallel platform. So in this subtopic, we want to look at what are the models that are available in order to data to communicate with each other between the processes. So there are two primary forms to exchange the data between the parallel tasks, either using shared data space or exchanging messages. Okay. So platforms that provide a shared data space are called shared address space machines or multi-processors. Multi-processors does not mean that multi-computers. However, the platforms that support messaging are called message passing platform or multi-computers. Okay, so the first one, shared address space platform. Okay, there are actually two types of platform in this model. The first one is uniform memory access, also known as UMA, and second one is non-uniform memory access, also known as NUMA. So if you use UMA, actually it has an identical time, and NUMA has not have the identical time. So part or all of the memory is accessible to the all processors because of what? It uses the shared address space. Processors interact by modifying data objects stored in this shared address space. Okay. So if the time taken by a processor to access any memory word in the system global or local is identical, so the platform is classified as UMA just now, and then or else is classified as NUMA or non-uniform memory access. So if you want to have the further explanation on UMA and NUMA, you can go to this website or YouTube. Okay. All right. So this is the diagram that represent the UMA with caches and also NUMA with local memory. So these three platform actually use the shared address space concept. Okay, as you can see here, UMA, this one is the processor and then the memory. It has a interconnection in the middle. So UMA plus cache, okay, to increase the speed of the processing, it has a cache here on each processor. Okay. And NUMA on local memory is required local memory in order to do the processing. Okay. Okay. Next one. The explanation on NUMA and UMA. The distinction between NUMA and UMA actually from the view of algorithm design. NUMA machines require locality from underlying algorithm for performance. Okay, that's why we look at the diagram just now. NUMA consists of local memory. Programming this platform is easier since reads and writes are implicitly visible to other processor. However, read-write data to shared data must be coordinated. We need to do some coordination because it's related with more than one processor and also memory. So caches in such machines require coordinated access to multiple copies. So cache also need to be coordinated to make it to ensure this cache, okay, can implement the uh, concurrent or parallel processing. So a weaker model of these machines provides an address map but not coordinated access. So these models are called non-cache coherent shared address space machine. Okay, so we look at the difference between shared address space and shared memory machine. Okay, so actually there is some difference between these two concepts. So we refer to the former, the shared address space, as a programming abstraction, and the second one, or the shared memory machine, as a physical machine attribute. So it is possible to provide a shared address space using a physical distributed memory. All right. So the second approach on how to make a communication between the data and also the processor during the parallel processing. The second one is called as message passing platform. So these platforms comprise of a set of processors and their own exclusive memory. Each of the processors has their own memory. So instances of such a view come naturally from clustered workstation and also non-shared address space multi-computers. So this is for purposely created or designed for multi-computers. Okay, this consists of more than one computers. So these platforms are programmed using variant of send and receive primitive. So libraries such as MPI and PVM provide this primitive. Okay, so message passing requires little hardware support compared to other platform, okay, other than a network. Shared address space platform can easily imitate message passing. So the reverse is more difficult to do in an efficient manner. Okay, so this is a difference between message passing and also shared address space. Okay, okay. So that's all for this lecture. So let's we recap a few things in this what we have discussed in this video. So first of all, we learned different kinds of platform to exchange the data or to in the communication model. So there is UMA and NUMA, shared address space, shared memory machines, okay, SIMD, MIMD. So and then in the earlier slide, we know there is a weakness or limitation when we use the what we call that the control structure of the parallel program. Okay, the increase of bandwidth. Okay, while we are trying to reduce the processing time, but we still can increase the bandwidth uh, when we do the parallel uh, computing. Okay, so that one is under the uh, subtopic of latency hiding. Okay, so hopefully you can get a few important things in this lecture. Okay, so that's all from me. Thank you.